once again, in this chapter we're going to look at tuning the virtual machine. We'll understand some of the main parameters that you can use as runtime arguments to the virtual machine to change its default settings or behaviour. And we'll see that there are 3 different types of garbage collector that you can use, called serial, parallel, and mostly concurrent. Java decides which is best based on your hardware, so we'll see how to find out which type your computer is using, and we'll learn how to change the type. So let's get started. By tuning, I mean providing command line arguments to the Java runtime so that one or more non-default settings is applied to our application. We've already seen one of the options on this course. We set the maximum heap size using the -xmx command line parameter. We found this to be useful to run our application with a limited heap size to assist in the detection of potential memory leaks. You might also choose to set a low maximum heap size to test that your application will run satisfactorily in a memory-constrained environment. More often though, we use -xmx to increase the heap size from the default. We can find out the default heap size by looking at the Java docs. I've got on screen here the relevant part of the Java docs for Java 8, and if you read down this you'll see that it says the default heap size is normally a quarter of your computer's total memory, although there are minimum and maximum values. If you're on a client rather than a server, then the maximum default heap size is 256 megabytes. We can see the default heap size that Java's using in the Visual VM tool. I've got a simple Java application running on my machine. Actually, it's an application that really doesn't do anything. It just has a never-ending loop that calls thread.sleep. I've created this application just so that I can have a program running which stays alive long enough for me to look at it in the Visual VM. And we can see in the monitor thread, which is what I've got here, that it has a heap size of 268 million bytes, which should be 256 megabytes. Although this is the maximum heap size when the application starts, it won't get allocated the full 256 megabytes of memory. There's a further default, which is the default starting size, how much memory is allocated when the application starts. Looking at the Java docs, we'll see this is set to a 64th of the total memory of your computer with a minimum initial size of 8 megabytes. We set the starting heap size by using the XMS command line option. It works the same way as XMX. We simply follow this by a number indicating the size of the heap size that we want, followed by either the letters K for kilobytes, M for megabytes, or G for gigabytes. So for example, if I want to run my application with a starting heap size of 150 megabytes and a maximum heap size of 512 megabytes, I'd provide a command line argument that would look like this. There will be some performance impact each time the heap needs to get more memory as it grows from the starting size towards its total size. So setting the starting heap size to the minimum that your application will normally need might be a good idea in performance critical circumstances. If you're running a server application where there won't be any other applications competing with yours for the memory of the machine, then you might choose to set the maximum and starting heap sizes to be the same. The information about these 2 parameters can again be found in the Java docs. The URL that you need is on screen here. You might notice in the URL it does say Unix. The version I've got up here is for the runtime environment that applies to Mac and Linux machines. If you change this Unix to Windows, I'll just do that just to prove it, I'll get the same page as it applies to Microsoft Windows machines. You need to scroll down this page to find the different command line arguments that we're going to look at. For the purposes of what we're going to cover in the course, they'll be identical whether you're using the Unix or Mac version of the Java runtime or the Windows version. All of the command line arguments that we're going to be looking at in this chapter can be found on this page, so if you want to know more information about any of them, you can look at this page. There is just going to be one that isn't on here, and we'll deal with that one next. Before we get to that though, I should just point out that these are the runtime arguments for the Oracle Java runtime. Now, most of these runtime arguments will have been implemented on every modern virtual machine, but if you are using a virtual machine that is different to the one provided by Oracle, then you might need to check that virtual machine's documentation to first of all ensure that the runtime argument has been implemented, and secondly that it works in the same way. The runtime arguments that start with the letter X, like the XMX and XMS arguments that we've already seen, are non-standard arguments, so they're not guaranteed to be implemented on every runtime. But let's have a look now at the parameter that is not on this page. I'm wondering if you can guess which one that is. The clue is that this is the Java 8 documentation, and the parameter that's missing is the one that allows us to set the size of the permgen space. You'll remember from the last chapter that permgen was removed in Java 8, and that's why it's not found in the Java docs at this URL. But if you're running a server app with Java 7 or below, then this is definitely one you'll need to know about. So to change the size of the permgen space, we use the command -xx max perm size. Note that all of these runtime arguments are case sensitive, so take care if you're using these to ensure you're getting the case correct. With the max perm size argument, unlike XMX and XMS, when you specify the size, you need to use the equal symbol. So for example, to set the size of the permgen for your application to be 256 megabytes, well, the code is on screen here that you'd need to provide as a runtime argument. The next option is useful if you want to monitor how often garbage collection is taking place in your application. We know that you can check this using the Visual VM application, but if you want a quicker way just to monitor it, this might be useful. The argument is -verbose :gc. The verbose argument does have some other options you can output, but these aren't related to memory or garbage collection, so I'm not going to cover those here. You can read the Java docs if you're interested. Just to see this one in action, I've come up with some simple code. You could pause the video and type this in if you like. It's not too exciting. What I've got is an array of customers and then a never-ending loop that adds a new customer to the array, and if the number of items in the array is greater than 100, then it removes 10 of the customers from the array. So we'll be every so often removing 10 items at a time. Those 10 items will then be eligible for garbage collection, and I expect if we run this with a reasonably small heap, then we should see some garbage collections happening relatively frequently. So if we right click on the application and do run as and run configurations, I think that option is just off screen. And in the arguments, I've actually typed in here a 10 megabyte heap. I want it to be very small. And then here's my -verbose :gc argument. So if we run this now, it's not terribly exciting. In fact, you can see we've already had 2 garbage collections straight away. My application is still running. I imagine we'll get another one in a moment. And there we've had a couple more now, and in fact they're becoming more frequent, so I guess that my application is probably starting to run out of space. If you're trying to fine-tune your application, you might want to alter the size of the young generation. That is, how much of the heap is occupied by the young generation versus the old generation. By default, the young generation is set to be 1/3 of the total heap size. If your application, like the one we've just seen, has very few objects that are going to survive into the old generation, you might want to increase the size of the young generation. Oracle recommends that you size your young generation between 1/2 and 1/4 of the overall heap size. The option to set the size of the young generation is the argument -xmn. This works just like the other XMX and XMS arguments we've just seen. For example, if you wanted to set the young generation to 256 megabytes, you'd issue the command -xmn256m. Note that this option sets the total size and the initial size of the young generation at the same time. So in this example, you'd need your overall heap size and your initial heap size to both be sufficiently greater than this figure. If you set your initial heap size to be 512M, then when your application starts, half the heap would be for the young generation. If your application crashes with an out-of-memory error, then you might want to select this next option, which is -XX: heap dump on out-of-memory. This automatically creates a heap dump file when you get an out-of-memory error. We can then load this file into the Apache Memory Analyzer tool that we've seen, and that gives us a useful way to analyze what went wrong. If you have a user who tells you that on a production system they're regularly getting an application failing with an out-of-memory error, this might be a good way to analyze what's gone wrong on that particular system. The final set of options I'm going to discuss relate to changing the type of garbage collector that your application is using. Now, I'm not going to be giving too much detail about this. I'm going to give you a very brief overview, but if you are interested, you can read more at this webpage. This page goes into quite a bit of detail about the different types of garbage collector, and it is a good place to start if you want to know more than what I'm about to tell you. So what I think you need to know is that the Oracle virtual machine has 3 types of collector called serial, parallel, and mostly concurrent. The serial collector uses a single thread to perform all the garbage collection work. Now remember that while garbage collection takes place, your application is paused. So it doesn't matter how many threads are in your application. It doesn't matter if you've got a single threaded or a multi-threaded application. All your threads will be on hold while the garbage collector runs. But if your computer is running lots of other applications, then the garbage collector will be competing with those applications for processing time. So I guess if you've got a computer with lots of applications running and not a huge amount of processing power, then your garbage collection process will be slower than on a computer where no other applications are running. The serial collector then is using a single thread, and that's normally the best choice for a single processor computer and for applications with small amounts of data. You can explicitly select this option with the -X: use serial GC command line argument. The parallel collector will perform garbage collections on the young generation, and you might remember these are called minor collections in parallel. That means that you'll have multiple threads running, all performing the garbage collection process. So that's going to be a useful option if you have multiple processors on your computer or processors that are able to process multiple threads at the same time. This option is normally good for larger data sets also, as it can give better performance than the serial collector. This collector is sometimes called the throughput collector, and you can select this option using the -XX: use parallel GC command line argument. And finally, we have the mostly concurrent collector. Now, the Java docs say that this performs most of its work concurrently. I don't actually think that's a terribly helpful explanation, and the way I understand the mostly concurrent garbage collector works is it's the closest we can get to a real-time garbage collection. That is where the application is not paused while the collection process happens. Actually, that isn't possible. Your application does need to be paused, but with this kind of garbage collector, I think of it that it pauses the application to do the marking of objects, but then resumes your application while the sweep phase takes place. Certainly the idea of a mostly concurrent is that the stop the world part of the garbage collection process is minimized. Now, if this isn't complicated enough for you, then I'm pleased to tell you that there are 2 mostly concurrent collectors you can choose from, the mark sweep collector and the G1 collector, and I'm showing you the command line arguments for each of those on screen now. I'm going to leave you to read up on the difference between these, as well as the Java docs. Searching the great Stack Overflow website for both of these phrases will give you plenty of discussions on the differences. So the final question you might be wondering at this stage is which garbage collector is being used on your computer by default. Well, Java makes this choice for you based on your hardware, but you can find out which garbage collector it's going to use by running the Java command with the -xx : print command line flags command line option to find out what that is. I'm going to do that now on my computer. So as you can see, I've typed in Java -xx : print command line flags. I'm just going to press enter, and the answer to this question is just here. I've got a command line argument of -xx : use parallel GC. So on this particular computer, Java's decided that the parallel garbage collector, or the throughput collector, is going to be the best choice for my machine. That covers the most useful options to tune the virtual machine. We looked in this chapter at a number of parameters that let us set the starting heap size, total heap size, the size of the young generation, and if you're using Java 7 or below, the size of the permgen space. We saw that it's possible to automatically make a heap dump file if your application runs out of memory. I think that's a particularly useful option if you have a problem on a live server that you're unable to replicate on the development machines. And finally, we understood the types of garbage collector available, the serial, parallel, and mostly concurrent collectors. And we saw how to find out which of these Java is going to use by default for your particular hardware. Coming up in the next chapter, there's going to be a final worked exercise where we'll be looking for a memory leak in a real-world scenario. So I'll see you in the next chapter.